All right, master plan part 3. The story, and I think this holds together quite well, and we'll be actually publishing a detailed white paper with all of our assumptions and calculations, is that there is a clear path to a fully sustainable Earth with abundance. In fact, you could support a civilization much bigger than Earth, than much more than the 8 billion humans could actually be supported sustainably on Earth. So we're going to walk through the calculations for how to create a sustainable energy civilization.
And to set the stage, today our energy economy, let's be honest, it's dirty and it's wasteful. Over 80% of global energy, primary energy, comes from fossil fuels, and only 1/3 of that global energy actually ends up delivering useful work or heat. This is the problem statement, but we're here to talk about the solution.
When we see people doing calculations for what does it take to create a sustainable energy Earth, they assume that the same energy amount is required for an electrified civilization versus a combustion civilization. This is not true, because most of the energy of combustion is waste heat.
Through end-use efficiency and through efficiency along every step of the way, actually the total energy use halves. So this is one of the most enabling aspects of electrifying everything, is that the sustainable energy economy is that much easier to accomplish. It's actually half the problem statement of the fossil fuel economy. So how the master plan works, you want to talk about?
So the thing that is needed at very large scale that is not currently present is a vast amount of battery energy storage. Our rough calculations are that this is about 240 terawatt hours, or 240,000 gigawatt hours. This is a lot of batteries, but it is actually a very achievable amount. We'll go into details on that.
Yep.
So that's a combination of electric vehicles and stationary storage. Now, if you look at the total world economy, it's just under 100 trillion. So if this was spread out, say, over 10 years, it would be 1% of the global economy. Over 20 years, it would be 0.5% of the global economy. So this is, not a big number relative to the global economy.
These are the 5 areas, and we're going to go into detail on all of them.
Yeah, I mean, my personal opinion is that as we improve the energy density of batteries, you'll see all transportation go fully electric, with the exception of rockets. That's awkward. But you can make the fuel with CO2 and water. So you can make methane with CO2 and water. So,
and in fact, you can do that with just electricity. So.
Yes, exactly. So, in fact, on Mars, if we hopefully get there at some point, the atmosphere is CO2, and there's water ice throughout Mars. So you can take the CO2 and H2O and turn that into CH4, which is methane, and oxygen. So ultimately, even rockets can be electrified.
So first, repowering the existing grid with renewables. And this is going to be a consistent theme. You'll see our estimates for the number of terawatt hours, terawatts, and trillions of investment at the bottom of the page. You know, this is already actively occurring in front of us. 60% of the generation added to the US grid was solar in 2022. And actually, on a year-on-year basis, solar deployment is growing 50% year-on-year. Second, switching to electric vehicles. Again, 21% reduction in fossil fuel use by doing this alone. Obviously, Tesla is heavily engaged in this activity, along with many others. Overall, EV production grew 59% year-on-year in 2022, and EVs hit an amazing 10% market share. I mean, it's an awesome milestone. I'm super excited to see that. And you can see the sort of breakdown of the fleet by millions of vehicles. You know, our goal is to do 20 million electric vehicles a year.
Yeah.
And one of the reasons why EVs are so enabling is this end-use efficiency point. Tesla Model 3, it's 4 times more efficient from the well to wheel than a Toyota Corolla. And that's all about the efficiency of getting the electricity into the car in a sustainable energy economy, and then how efficient the car is in transferring that stored energy to motion on the road. Switching to heat pumps in homes, businesses, and industry. You know, right now heat pumps meet 10% of building heating needs. Install rates growing 10% year on year. It really needs to accelerate. Heat pumps can serve, you know, heat applications up to 200 C in businesses and industry. And from an investment perspective, as you can see on this page, this is actually the lowest hanging fruit in terms of displacing fossil fuels. You might be saying, well, what exactly is a heat pump? So heat pumps don't move heat, don't create heat, they move heat. When you think about like the natural gas furnace in your house, like it is generating heat itself, but what the heat pump is doing is actually moving heat from outside of your house into your house. They're just an air conditioner or a refrigerator in reverse. So we're surrounded by heat pumps. There's like, they're all over this factory. They're in your house. And all this really is about bringing them to displace all the fossil fuel heating in all of the homes, business, in the industry. Next, a little bit more detail on electrifying high-temp sort of industrial chemical processes. So over 50% of industrial heat is greater than 400 C. Cement, steel, fertilizers, chemicals, plastics, metals refining all need like 1500 C. So we need a solution here. Ultimately, it's purpose-built equipment that enables electrification. Carbon graphite is stable up to 2800 C. There's other options in the 1500 C range, like silicon carbide, other materials. So the idea here is you create and store heat when renewable power is available. If this is a sustainable energy economy, renewable energy is intermittent. Peak of the day, you've got more generation than you need. You make a bunch of heat then, and then you transfer that heat into the industrial process 24 hours a day using the stored heat you created when the sun or the wind was blowing. That's the concept here. And then on the hydrogen side, we also need green hydrogen to decarbonize metals and chemical refining processes. This is things like ammonia, making steel. There's roughly 120 million tons of hydrogen sourced from fossil fuel today to do these things. And hydrogen can also directly replace coal, which is currently used in a ton of steel production, through a process called directly reducing iron. You can replace blast furnaces with a hydrogen-reducing direct reduced iron furnace. And this is the way to eliminate fossil fuels from these aspects of the economy. A small part of the pie, but a necessary part of the pie, is sustainably fueling planes and boats. Shipping accounts for 3% of global CO2. It's ripe for electrification. Even with lithium iron phosphate, long-haul ships can be fully battery-powered. So that's a great opportunity to electrify. Energy density is a little bit harder for planes, but short-haul is doable today. With some improvements, we'll get long-haul underway. But even in the meantime, we can leverage sustainable aviation fuels produced and stored using excess renewable electricity. There's a lot of work going on in this space. So when we stack up all of these efforts, we end up with the numbers we shared at the beginning of the presentation. 30 terawatts, 240 terawatt hours, $10 trillion. And you may be saying, like, I need some context. Is this feasible? Spoiler alert, it's entirely feasible. Just looking at it from a growth rate perspective, how much do we need to grow the deployment of these technologies? We're talking about only a 3x growth rate in solar and wind deployment. Solar is already growing at a breakneck pace, as is wind. This gap is going to be closed really quickly. When we look at the electric vehicles, they have to grow 11x. Well, they grew 60% year on year last year. That growth rate is also going to close pretty darn. That gap is going to close pretty quickly as well. And lastly, storage. Tesla's energy storage business has grown at 65% CAGR since 2016. The global, energy storage business is accelerating pace as well. I mean, all these gaps are going to close, especially as this momentum of the transition to sustainable energy accelerates. And then, what about this investment? How do I have a reference point on this investment? Elon mentioned it's 10% of, 1 year's world GDP. Another way of thinking about it is how does it compare to what we're investing, like what we invested last year in the fossil fuel infrastructure? And it's 60% of that investment. So actually, building this sustainable energy economy is less than extending the fossil fuel economy from a year-over-year investment basis. So very doable. Land area intensively farmed today is 12.5% of all land. So, I mean, you drive around, you see some farms, but you don't see them everywhere. This is an order of magnitude, more than an order of magnitude difference between farming and what we're talking about for sustainable energy land. The resources are there to support the transition. This is cumulative demand to move in the sustainable energy economy direction until 2050 relative to USGS resources today. History teaches the more we look, the more we find. What people think happens is, oh, there's this many resources, next year there's going to be less because we're going to extract them. What actually happens is, As we extract resources, we find more. And you can see on the right what has actually occurred with the key materials to the sustainable energy economy. Since 2000, as the sustainable energy economy has been growing, and Tesla's been growing, and all the industries around us have been growing, the actual resource availability has increased, not decreased. We're doing this to build this sustainable energy economy, but the maintenance amount of ore that we require is really an order of magnitude or more, less, because of recycling.
Hi.
Hi, I'm Franz. I lead design at Tesla.
And I'm Lars. I've been doing vehicles with Franz for almost 13 years now. After all that, we would design, engineer, manufacture, and plan for automation happening together. It gives us the opportunity to question requirements. This is something that is fundamentally only available at Tesla. The traditional way of making a vehicle is this. You stamp it, you build a body in white, you paint it, and you do final assembly. And what's interesting is these shops are dictated by the organizational structures that exist. And they're dictated by the boundaries that exist in the factories that are laid out. If something goes wrong in final assembly, you block the whole line, and you end up with buffering in between. And when you watch it happen, it's actually really silly to a guy like me. You take all these stamp panels, you put them together, then you put them in a framing station, you build a body that looks something like a car, you put the doors on, and then you paint them. Once you get the color, you take the doors off, and then you start putting the interior inside the car. It comes in through the openings that already exist. I wish it went in like this big piece like this, but there's actually people coming in and out of the car. There's awkward movements. Then we lift the car up. We put stuff from underneath it. We put it down. Then we put the seats in the car. And finally, we close it all out with glass, and we bring those doors that went away for a trip, and we put them back in the car. Most of the time, we're doing this with a big, giant car and moving it and doing really nothing to it at all. As part of the master plan, we have to make another step change in cost. We started this on Model Y when we made these huge gigacastings, and we deleted hundreds of parts. We simplified assembly with the Model Y structural battery, where we decided the floor should be a part of the car. The battery is the floor. We put the seats and the interior on the battery, and we bring it up through a big open hole, and we assemble it. And this allowed us to do things in parallel, fully rethinking the process and reducing the final assembly line by about 10%. And we thought maybe we could do this other places.
Yeah, I mean, in a way, the constraints become part of the solution rather than a problem.
So when you think about what I'm trying to say, I really want to hammer this home. When you have a car that's about 5 meters long, and you have people working around it like we did in Model 3, and we change that to this process where we take different parts of the car, and we can do more at the same time, like we did with the Model Y structural battery pack. What you see here is us doing that on the front part of the vehicle, or the rear part of the vehicle. That means we can get more people working on the car, or robots, working on it at the same time. That means we have better operator density, less time doing nothing. I call that space-time efficiency. It has nothing to do with quantum mechanics. We can have that conversation later. In the end, that will probably look something like this, where we balance parallel and series manufacturing in a way where we only do things that are necessary, with a much shorter final line, blocking a lot less of the entire rest of the factory, so we can optimize material flow using the best practices. And what that means, it's going to look something like this, where we build all the sides of the cars independently, we only paint what we need to, and then we assemble the parts of the car once and only once. We put them where they need to go. The interior is attached from a bottom-up or a top-down strategy, so there's more access for those robots and people. We aren't moving heavy objects around and doing nothing to it. And it means we're doing more work on the car more of the time. And then when we take all of these tested sub-assemblies and we put them together, we finally assemble the car only one time, putting the sides on with all of their parts to a front and rear that was already assembled, carrying the floor in with the seats, and finally boxing it out with the doors one time, just like Cybertruck. So in the end, you get the same car, but it's not going to be a Model Y.
Yeah, this is not. Yeah. This is a Model Y for illustration, not the next-gen vehicle.
To increase the scale and adoption of electric vehicles on the orders of magnitude that we just showed you, we have to make constraints part of the solution. It leads us to greater than 40% reduction in footprint, which means we can build factories faster, with less CapEx and more output per unit.
Thank you, Franz. My name is Colin Campbell, and I have the real privilege of leading powertrain engineering here at Tesla. And the other thing that you probably all know about our powertrains is that they're efficient. Our cars go 25 to 30% further than other EVs in our class for the same amount of efficiency. But at Tesla, efficiency means more than just reducing how much energy the cars use. It's about how we develop, how we manufacture, how we refine, and how we scale the powertrain. Now, the Model 3 and Y powertrain is a great example of this broader meaning of efficiency. So since we launched it back in 2017, we've continuously improved that powertrain and the factory that builds it. Inside the charger of your Tesla are transistor packages, and that's at the top of your screen here. And every electron that moves you down the road flows through one of these packages. We designed our own custom package, which is what you're seeing here, and we can extract twice as much heat out of that package as what we could buy off the shelf. And so what does that mean? It means that the silicon carbide wafer that's inside those packages can be much smaller. And silicon carbide is an amazing semiconductor, but it's also expensive, and it's really hard to scale. So using less of it is a big win for us. So in addition to the work that we've done in software and hardware, we've also done a lot of work in-house on software. So this is the drive unit for Model 3 and Y, and if we take a cross-section, we see the stator and the rotor, and they're responsible for the core function of the drive unit, which is converting electricity into motion. And our custom software lets us simulate the rotating magnetic field that is responsible for that conversion. And getting that simulation exactly right, it's central to the cost, the weight, the size, and even the sound of the drive unit. And now, you can buy software that will do all of this, but our tools are faster, and they're more accurate, and that was not easy to do. And that allows us to quickly iterate through millions of possible drive unit designs to find the best one. So at Tesla, our powertrain and our powertrain manufacturing equipment is both designed under one roof. The engineers who are designing the motor, they are in the same room as the engineers who are designing the machine that's going to put that motor together. And that collaboration pushes us from day one to design products that are not only high performance, but are really easy to assemble. So those silicon carbide transistors that I mentioned that are key component but expensive, we figured out a way to use 75% less without compromising the performance or the efficiency of the car. And of course, we know that battery cell supply is one of the constraints on the scalability of EVs right now. Our new powertrain is compatible with any battery chemistry. And that will give us great flexibility in battery sourcing. If we want to make EVs more accessible to people, they have to be cheaper. We've reduced the drive unit cost to about $1,000. And we don't think any other automaker is even close to that number. Finally, the bigger a factory is, the longer it takes to build. If we can build the same number of cars from a smaller factory, we are going to be able to scale EV production faster. Our next powertrain factory is 50% smaller than the one that's behind me today, even though it has the same capacity. So I talked about how we had reduced the amount of rare earth in our powertrains. And as the world transitions to clean energy, the demand for rare earth is really increasing dramatically. And not only is it going to be a little hard to meet that demand, but mining that rare earth, it has environmental and health risks. So we want to do even better than this. We have designed our next drive unit, which uses a permanent magnet motor, to not use any rare earth materials at all.
Thanks, Colin. Good afternoon, everybody, and welcome to Texas. One of the changes that we're looking to make right now is to change something that's been steady for the last 60 years, 12 volts. 12 volts has been, as I said, for 60 years. The demand for power in the car has been steadily increasing to the point where we now have to have pretty large wires to drive over 200 amps of current around the car, which increases the mass and cost. With Cybertruck and all future Tesla platforms, we will be moving to 48 volts. This reduces the current needed by a factor of 4. And since power loss in the harness is resistance times the square of the current, a 4x reduction in current leads to a 16x reduction in lost power while distributing energy in the car. That allows for smaller wires, smaller e-fuses, and smaller controllers, It also allows us to make those heat sinks smaller, or in many cases, remove it completely, all benefiting the car in terms of mass and weight. 48 volts is the future for low voltage design at Tesla, and likely the rest of the industry in due course.
We welcome and encourage other OEMs and the entire supplier network to join us on this evolution.
You bet. For the next-gen platform, we're looking to optimize the controller design across the entire car and across all of the organizations, not just for a given subsystem. Simplifying the wire harness will enable automation. 48 volts will allow us to reduce the size, mass, and cost of the low-voltage system, and it's one of the key things to enabling us to scale production of the low-voltage systems for the Master Plan 3.
So I joined Tesla in 2012, and even in those very early days of the Model S, we already had the ability to update software over the air in all of the controllers throughout the entire vehicle, at a time when other cars were just starting to update software in only their infotainment units. We are able to use our collision data to design our crash safety systems for what happens in the real world, far beyond what regulatory and consumer ratings tests prescribe. And then furthermore, we're able to use that data to recreate in simulation all of those crashes every single time we make a change to the vehicle's design, or to the software that controls the airbags and other restraint systems. Here on this graph, the gray dots that show up first are specific crash tests that are prescribed by regulatory and consumer ratings agencies throughout the whole world. And the rest of the color that fills in around and on top of it, those represent the crashes that we've seen happen in the real world. Those are what we design for and what we test to.
Right. And last year, this data was used to change the algorithm for seatbelt tensioning to reduce injuries in the field, which was OTA to all of our cars.
So far, you've heard me talk a lot about how we leverage our software systems to iterate quickly on the customer-facing product. But what I haven't talked about, and what we haven't said much about publicly in general, is how we leverage these capabilities in our own internal operations. So for example, in the early days of manufacturing Model S, we very quickly realized that there are a lot of different ways you could misassemble a car. You could forget to plug in a wire, you could not fully set a connector, you could pull a part from the wrong bin. So when we designed our manufacturing processes for Model 3 and all of our other vehicles going forward, we took a page from the software playbook, which says, test early and test often. And we applied that mantra to every single car that we build at every step of the assembly line. So now, when a production associate plugs something into the car, the central car computer sees that connection, confirms that it's the correct part for the type of car that's supposed to be built, installs a software update if necessary, checks configurations and calibrations, and runs a barrage of tests on that thing and all the other things that are connected to it. And if it finds an anomaly that can't be fixed purely with software, it throws an alert immediately that is displayed prominently on the vehicle's display, as well as sent to back-end command and control systems, so that a human can come over and fix the problem before the rest of the car gets built on top of it. So that's a bit of a preview of all the pieces that we're building, looking ahead to our future of autonomous fleets. Synchronization, permissions management, security, and privacy. And that has been a whirlwind tour through some of the things that we're doing behind the scenes to enable the efficiency, cost reduction, and speed that we are going to need for our next phase of growth and for the next phase of the master plan. And so now, to tell us about the latest in full self-driving, I'd like to introduce Ashok.
Thanks, David and Pete. At Tesla, we are betting on AI, machine learning neural networks to help us build a general vision and planning system. So we don't stop at the computer vision techniques, but we reach out to techniques in other areas, such as language modeling, reinforcement learning, to model this task. This is similar. These networks use similar techniques, such as transformers, attention modules, autoregressive modeling of tokens, similar to what large language models like ChatGPT do out there. With such an end-to-end system of solving perception, we have really removed the brittle post-processing steps and produce high-quality outputs for the planning system. This is, for example, an intersection where we have to turn left while yielding to crossing objects and to the pedestrians crossing the road. We have to do this both safely and smoothly while respecting everyone's right of way and preferences. If this was done naively, each configuration would take 10 milliseconds of compute, and there are easily thousands of configurations to reason about. This would not be feasible using traditional compute. But using AI, we have packaged all of this into a 50 millisecond compute budget so it can run in real time. The second big piece of this puzzle is the data. This is where Tesla has a unique advantage because it can tap into the fleet to access the exact data that can fix the problems. But raw data is not sufficient. In order to train these networks, you need labeled data. You need labels to supervise the networks. And if you only depended on the human labelers, this data would be too tiny to train these large multi-camera video modules. We need lots and lots of data to train these networks. Hence, we have built a sophisticated auto-labeling pipeline that collects data from the fleet, runs computational algorithms in our data center, and then produces the labels to train these networks. Here, you are seeing a 3D reconstruction that is happening by collecting various clips from different cars in the fleet and assembling them, all of them together into a single unified representation of the world around the car. You can see all the lanes, the road boundaries, curb, crosswalks, even the text on the road being accurately reconstructed by these algorithms. On the chart on the right side, you can see that every time we add data, the performance improves. And then we can do this for every kind of task that we have in our system. And this is what we call as data engine. We identify challenging cases, such as the one you saw earlier, and there could be other different types of challenging cases too. We mine the fleet for such data, put it through our auto-labeling system, and produce the labels, add it to the training set, and once we have the newly trained models, we deploy them to the fleet. We have already shipped our FSD beta software to pretty much everyone that has bought it in United States and Canada. This amounts to roughly 400,000 customers who can turn it on anywhere, and then the car would attempt to drive to the destination. It's still supervised, but it can already handle turns, stop at traffic lights, yield with other objects, and generally get to the destination. We have observed that people who use FSD are already 5 to 6x safer than the US national average. Like I mentioned earlier, the solution to scalable FSD is getting the AI architecture, the data, and the compute just right. And we have assembled a world-class team to execute on this. We are pushing the frontier on these three items, and as we improve the safety, the reliability, and the comfort of our system, we can then unlock driverless operations, which then makes the car be used way more than what it is used right now.
It's obviously not doing parkour, but it is walking around. And we have multiple copies, I suppose, of Optimus. The thing that I think Tesla brings to the table that others don't have is that we have the real-world AI. We're the most advanced in real-world AI. So the same AI that drives the car, which you can think of the car really as a robot on wheels, and this is a robot on legs. So as we solve real-world AI, and I don't think there's anyone even close to Tesla on solving real-world AI. That same computer and software goes into Optimus. It's not even clear what an economy means at that point. Since an economy is output per person times persons, but if output is much higher and there's no limit on persons, then what's the actual limit on the economy? We're still pretty far from Kardashev scales here, but we're getting there. So anyway, it's probably the least understood or appreciated part of what we're doing at Tesla, but will probably be worth significantly more than the car side of things long term.